but has also made significant contributions to statistical research. His scholarly pursuits have resulted in the publications of two renowned edition volumes, namely Handbook of Applied Econometrics and Statistical Inference, and some recent developments in statistical theory and applications. Additionally, his extensive portfolio includes approximately 100 research papers published in esteemed national and international journals. His research interests are wide ranging, encompassing shrinkage estimation in linear models, dynamic models, panel data models, data mining in bioinformatics, Bayesian unit, root and co-integration tests, and control charts for autocorrelated data. His dedication to exploring emerging statistical methodologies is commendable and has undoubtedly advanced the field. Beyond his academic achievements, Professor Chaturvedi has extended his reach globally. His intellectual curiosity has led him to visit esteemed institutions around the world, including Pantheon Assas University of Paris, University of Wollongong in Australia, Bond University in Gold Coast, Australia, City University of Hong Kong, Tilburg, in the Netherlands, and several others. As a visiting research fellow, visiting lecturer, and visiting professional fellow, he has fostered international collaborations, further enriching his research and promoting cross cultural exchange. Today, we have the privilege of benefiting from Professor Chaturvedi's vast knowledge and experience. I urge all of you to seize this opportunity to engage in the meaningful discussions, learn from his insights, and exchange ideas. Let us embrace this occasion as a platform for intellectual growth and collaboration. Once again, on behalf of Christ Deemed to be University, Yashwantpur campus, I, Chavi Tiwari, extend a warm welcome to retired Professor Anoop Chaturvedi. We are truly honored to have you with us and we eagerly await your valuable contributions to our academic community. Welcome, sir. Over to you, sir.
Okay, can you hear me? Yeah. Hello?
Yes, sir. Yes, sir.
Hello, yes, sir. We are able to listen you.
Okay, thank you very much for your kind invitation and giving me opportunity to interact with your students and faculty members. Uh, Let me share my screen first. Uh, Just wait a minute. I have to share my screen. Now, can you see my screen?
Yes, sir. Yes, sir.
You are
So,
audible, sir.
okay. So in this lecture, I will speak on time series and its applications. Let me start with this simple example. Say, suppose you have two different sequences of observations. In first set of observations, say you have taken the observations as the outcomes of 100 rounds uh, of, say, if you are going to a casino and you play on a roulette wheel, and then you take the observations on the outcomes, and then you have, say, 100 outcomes. Then the second set of observations is the closing prices of a stock for 100 consecutive days. So you have these two sets of observations. Now, what is the basic difference between the nature or characteristics of outcomes of these two experiments? So in this first set of observations, if you have the knowledge of first two observations, say y1 and y2, does it give any information about y3 or y4? No, because different observations are independent of each other. So if your roulette wheel is fair, it is not biased, then different observations are independent, and the past observations don't have any information about the future observations. So for predicting any future outcome, there is no point in using the knowledge which you gain from the past observations, unless you observe some kind of pattern. in the outcomes, or unless the observations have some kind of correlation, or the observations are not independent. In the second set of observations, you have taken 100 observations for 100 consecutive days. Say a stock price of any particular day. It depends upon the past observations also. You cannot say that different observations are independent of each other. So the past observations may have some information about the future observation. Now, this is the basic difference between say usual IID observations or identically independently distributed observations and time series observations. In most of the statistical inference procedures, say in testing of hypothesis, in estimation, etc., our initial assumption is different observations are identically independently distributed. So the past observations don't have any information about the future observations. Whereas in time series observations, you take observations through time, and the observations may have some kind of pattern. The past observations may have some information about the future observations. So most of the classical statistical inference procedures assume that the observations are IID, identically independently distributed. Then in cross-section data, we take observations from different individuals or from different groups or from different units at a single point in time. So time does not matter. Whereas in time series data, you have a chronological sequence of observations recorded at specific time intervals over a period of time. Usually we take the time intervals to be equally spaced. And another feature of time series data is data at adjacent points are dependent. So for cross-section data, some of the statistical inference procedures are, say in testing of hypothesis, we use t-test, chi-square test, etc. Or you can use different analysis of variance techniques. In ANOVA also, we assume that different observations are identically independently distributed. But since in time series, different observations are dependent, so you require some alternative procedure for exploring the data. Ultimately, what is your objective? You have to extract information from the data. In classical inference procedures, ultimately we use different estimation procedures, different testing procedures for exploring information from the data. In time series, we require some alternative approach, some approach which is different from the classical statistical inference procedures. Now here are some examples. Say, suppose you take closing prices of a group of 20 different tech stocks on 30th June 2023. Now this is your cross-section data. You have 20 cross-section units on which you are taking observation at a single point of time. Our data on maximum temperature, humidity, wind speed of 13 coastal districts of Tamil Nadu on a particular day. So you have taken observations on 3 variables: maximum temperature, humidity, and wind speed. And your cross-section units are 13 coastal districts of Tamil Nadu. Or stock returns earned by shareholders of TCS, Infosys, and Reliance Industries as for the year ended on 31st December 2022. So again, you have 3 cross-section units on which you are taking observations. So these are some examples of cross-section data. Of course, you can get some information from these data, but you miss a lot of information, like whether the stock returns of different companies are increasing or decreasing over time. At a particular point of time, you can say that stock returns of TCS are more than that those of Infosys or less than, etc. But whether those stock returns that have some increasing or decreasing trend, or how these stock returns are performing over time, that kind of information you don't get using the cross-section data. Of course, in time series, you get set of observations collected at usually discrete and equally spaced time intervals. Usually, we take equally spaced time intervals. Then here are some examples. Daily closing price of TCS recorded over the last 6 months. Now you have time series data. So now you can draw inferences like how the TCS closing prices are performing over time during last 6 months, whether the prices have some kind of increasing pattern or decreasing pattern, etc. Weekly sale figures of coffee at a coffee shop during January to December 2022. Again, you have time series data. So you can observe some kind of pattern, whether the sale is increasing or decreasing, or whether the sale is increasing during certain months of, say, winter and decreasing during summers, etc. Such kind of inferences you can draw from this time series data. Or the quarterly data on GDP of India during 1980 to 2022. Again, using this time series data, you can draw inferences about how the GDP of India is performing over this period of time. Or daily data on number of COVID patients in Karnataka during 2020 to 2022. So these are some examples of time series data. So basically, in time series data focus on the same variable over a period of time, while cross-section data focus on several variables at a single point of time. Then sometimes we also have panel data. Of course, in this lecture, I am not going to cover this topic in detail, but sometimes you may observe time series data taken on different cross-section units. So you can have time series data on the stock prices of TCS, Infosys, Wipro, etc. So you have different cross-section units, and on different cross-section units, you have time series data. So such kind of data is called panel data. So in practice, actually, it is very important to identify the correct type of data, and it is also important to collect the correct type of data. Because the kind of inferences which you can draw from cross-section data, you cannot draw from the time series data. On the other hand, the kind of inferences which you can draw from time series data, you cannot draw using the cross-section data. Further, for different type of data, you require different statistical tools. For cross-section data, for exploring information from the cross-section data, you require different kind of statistical tools. For extracting information from the time series data, you require different kind of statistical tools, different kind of models, etc. And important to collect the correct type of data. What is your objective? Say, suppose your objective can be served by time series data, but you are collecting cross-section data. So it is also important to collect the correct type of data, keeping in view your objective. What is your objective? For what purpose you need the data? Now, this time series analysis includes methods for analyzing time series data to extract meaningful characteristics. What are the main characteristics of time series data? So you want to extract those characteristics, and for that purpose, you require different tools, different methods. Study the past behavior of the underlying phenomena, say probability mechanism or probability model, generating the series. So you have past observations, and you want to make inferences about the probability mechanism or the probability model which has generated those past observations. And once you identify the proper model or probability mechanism generating the series, then you can use that probability model for making future predictions. Then analyze the nature of the variation and identify the pattern of the observed time series. What is the nature of the variation? Whether sale of coffee increases during winters or not. So it has, suppose you observe that each year during winters, the sale of coffee increases. Then accordingly, you have to plan your strategy. You have to increase the supply of coffee during winters. So basically, you want to identify the pattern of the observed time series. Then the established pattern can be used to forecast future values. So once you identify the pattern of the time series, then you can use that pattern for forecasting purposes. Of course, it is quite natural that far off in time we try to predict, the less accurate is the forecast. Say, suppose you have past observations on the population of India, and you want to forecast the population of India in 2030 or 2050, then obviously your prediction for 2030 will be more accurate than the prediction for 2050. Then why we need time series analysis? To understand underlying trends or systematic patterns over time. Then to interpret these features and then dig deeper to assess the causes of the pattern. Say in particular months, the sale of coffee increases. Then what is the cause? Whether it is season or it is increase in the number of tourists, etc. So once you identify the pattern, then you want to assess the causes of the patterns. Then use time series forecasts to predict the likelihood of future events and likely changes in the data along with the margins of error. So obviously you want to forecast the future values. And you are also interested in what is the likely margin of error. Say it may have 5% error, 10% error, etc. Make inference about the probability model generating the series, develop confidence intervals and hypothesis tests on model parameters. So say you can use confidence intervals for estimating the margins of errors. You can use the probability model generating the series for forecasting purposes, etc. Now here are many several applications of time series for economic forecasting purpose. You can use economic time series. For financial market analysis, you require financial time series. For marketing and sales forecasting purpose, whether sale is going to increase during summers or it is going to decrease during summers, whether you require more infrastructure during summers because of an increase in tourists or during winters because of increase in tourists, etc. Then census analysis. For yield projections also we use time series analysis. For weather forecasting, we use different time series models. Stock market analysis, insurance benefits prediction, forecasting the number of sales or claims in the insurance sector. So it has applications in various areas. Network data analysis, network users prediction. So how many users you expect during next month or during next year, etc. So accordingly, you have to manage your infrastructure. Process control for the chemical and process manufacturers. Now even time series models are also used in process control, in quality control. Signal processing, to distinguish between signals and noise. So it has applications in various areas. Well, here I have given some examples. Just I have plotted the graphs of some time series. So basically, time series consists of distinct patterns, mixtures of patterns, and your objective is to identify these patterns. And if you can identify these patterns, it makes easier to make predictions. So here is the graph of electricity generation in India. Now, just by looking at this graph, you can draw various inferences. And if along with this time series, you also have the time series of consumption of electricity, then means it may be even more useful for you. So, and on the basis of this graph, at least you can say that the generation is increasing. At what rate it is increasing, you can assess. It has decreased during certain periods. You may try to explore the reason why it has decreased during this period or during this period, etc. Now, this is the graph of monthly totals of US airline passengers from 1949 to 1960. You can easily identify that there is an increasing pattern, but within this increasing pattern, you observe these cycles. Now, it may be because of some seasonal effect. More people prefer to visit some places. There are more tourists during these periods. So you can easily observe the pattern of the data. So at least you can draw some inferences, but just by looking at the graph, you cannot make very accurate predictions. You can guess the future values, but you cannot make very accurate predictions. Now, the traditional approach for analyzing all these variations or for analyzing the time series is to decompose the variation in four major components: secular trend, seasonal component, cyclical component, and then you have some irregular pattern or random component. So the data has a long-term movement, increasing pattern, which is called the secular trend. Then within year, you have some uh, these cycles. So this is actually a seasonal pattern. And then sometimes you have cycles with period more than 1 year. So such kind of components are called cyclical component. And then you have some irregular components, some irregular variations. So the classical approach was based on the decomposition of variation into these four components. Well, I am not going to into much details of this classical approach. My objective is to discuss the Box-Jenkins approach, which is now more popular. And let me consider this bivariate data. Now, many of you must be aware with the correlation and regression. So for bivariate data, we calculate correlation coefficient, and then you can also fit the regression. What we do in regression, you have an input variable, say X, and an output variable, Y. And suppose there is high correlation between X and Y, which is desirable in regression. Then you can fit a regression function or regression line between Y and X. Then the regression line gives a good prediction of y based on x. So if you have the value of input variable, then you can use that input variable for predicting y. So basically how we proceed in the regression, if x and y are highly correlated, then we try to estimate, say suppose you are fitting a regression line, then we try to fit a linear function between y and x on the basis of past data. And then if the regression line is good, if it provides the proper fit, then you can predict y on the basis of given value of x. Now, highly correlated xy means x has information about y. And if x has information about y, then it is helpful in predicting the value of y. Now, in time series, a basic feature of time series is different observations are correlated with each other. The present observation is correlated with the past observations. What does it mean? It means the past observations have information about the present observation, or the observations are up to the present data have information about the future. So since the past observations have information about the future, the question arises, is it possible to utilize this kind of correlation in time series observations to get improved forecasts? And if yes, then how you have to proceed? Say in regression, how we proceed, if x has information about y, then we fit a function between y and x. Say we fit a straight line between y and x. And then we use that straight line for predicting y on the basis of x. Now this is how we proceed in time series also. Since the past observations have information about the future, so if we can fit a proper model between the present information and the past information, or the present observation and the past observations, then you can utilize that model for the prediction purpose. Now, this is actually the basic idea behind Box-Jenkins approach. In Box-Jenkins approach, basically we try to develop model between the present and past values of time series and the shocks. So it aims at rigorously studying the past observations on a time series. So we try to develop an appropriate model describing the inherent structure of the series, just like regression. Then evaluation of properties of the probability model. So once you have fitted the model, then you can study the properties of the probability model, generating the time series. And then you can use this model for future forecast purpose. So these are the basic steps of Box-Jenkins approach. We develop an appropriate model, we evaluate the properties of the probability model, and then we make use of this model for making future forecasts. Now, before moving ahead, let me describe some of the measures. A mean function, which is defined as expectation of yt. Variance function is the variance of yt. And autocovariance function is the covariance between yt and yt plus k. So obviously, if we take k equal to 0, then we get gamma 0t, which is equal to variance of yt. We can also define the autocorrelation function of lag k as rho k t equal to gamma. This is the covariance between yt and yt plus k. This is the variance of yt and variance of yt plus k, and then we take to the power half, just like the simple correlation coefficient. And if we take k equal to 0, then we get 1. Now, in practice, suppose we assume that mu t is equal to mu for all t, sigma square yt is equal to sigma square y for all t. And gamma kt is equal to gamma k. Again, it does not depend upon t, it depends upon k. K is the lag, means gamma kt is the covariance between yt and yt plus k. So t plus k minus t is equal to k. K is the lag. And ACF also depends upon k only, it does not depend upon t. Then in practice, suppose you have these observed data. This is the observed time series, y1, y2, yn. Then this is the sample mean. We add all the observations divided by n. You can define sample auto covariance function of lag k. Actually, you get n minus k pairs like this. y1, yk plus 1, y2, yk plus 2, and so on. And notice that in each of these pairs, what is the lag? K plus 1 minus 1 is k. K plus 2 minus 2 is k, and so on. And then we calculate the covariance, Ck. So you have n minus k pairs, and then you take t, summation t equal to 1 to n minus k, yt minus y bar, yt plus k minus y bar. And if n is large in comparison to k, you can approximate it by this formula. So this is how we define sample auto covariance function, and similarly you can define the sample auto correlation function of lag k. Rk is equal to Ck upon C0. And if you plot Rk against k, such a graph is called the correlogram. And what is the use of this correlogram? Actually, when we come to different models, you will observe that this autocorrelation function plays an important role in model identification. Or this correlogram also. This plays very important role in model identification. And another tool which I am not going to discuss here in details is partial autocorrelation function. It is just like the partial correlation coefficient. Here you have calculated the simple correlation coefficient. In partial autocorrelation function, we calculate partial autocorrelation coefficient. This also plays very important role in model identification. So whenever you fit a time series model using any statistical software, normally it gives you the plot of correlogram as well as the plot of partial autocorrelation function. And you can use those graphs for model identification function. Now, first, let me define a purely random process or white noise process. Now, suppose UT is a sequence of identically independently distributed random variables. then this is called a purely random process. And usually we take its mean equal to 0. Since random variables are identically distributed, so all UTs have same mean and same variance also. So we take the variance as sigma square u for all t, and auto covariance function gamma k is equal to 0 for all k greater than or equal to 1, because different observations are independent of each other. So different observations, different UTs are uncorrelated. Independent means different UTs are uncorrelated. And if you plot ACF, or if you consider ACF rho k, this is equal to 1 for k equal to 0 and 0 for k equal to 1 to so on. Now, this is a specific feature of purely random process. Or this is also called white noise. Why is it called white noise? Because if you consider the spectral density function of purely random process, then it is uniform. And those of you who have studied physics, they may be knowing that the white light also has a spectrum which is uniform. Now, let us see how this particular feature of ACF serves the purpose of identifying a purely random process. For that purpose, you can do one experiment. You just draw a large random sample from any, say, normal distribution with mean 0 and variance, sigma square u. You can take sigma square u equal to 1 or 4, whatever. And then you plot the ACF of that series. You will observe this kind of ACF. So all these values are very close to 0. So just by looking at this ACF, you may conclude that your process is a purely random process. This is how the plot of ACF helps you in identifying the process. So if you believe that your process is a purely random process, then you just plot the ACF, and its ACF should be like this. Now suppose you have a time series, then how y has evolved. At a particular point of time, say t, you have observations up to time t minus 1. And then up to time t minus 1, u1, u2, so on ut minus 1. These are the random shocks or white noise up to time t minus 1. And ut is the random shock at time t. Now there are different possibilities. Process has a memory of random noise corresponding to past values of y, but no memory of where it or y was, means the past values of y. Process has a memory means the value of y at time t, say yt, it directly depends upon random noise corresponding to past values of y. Random noise corresponding to past values are u1, u2, so on, ut minus 1. but it has no memory of where it or y was. Means it does not have memory of y1, y2, yt minus 1. The second possibility is process has a memory of where it was, means past values of y, but no memory of random noise corresponding to past values of y. It has no memory of u1, u2, ut minus 1. Of course, ut is going to affect yt. So ut will always be there. The present shock is definitely going to affect the present observation. And the third possibility is process has memory of past values of y as well as memory of random noise corresponding to past values. So these are the three possibilities which led to the development of three time series models, which I am going to discuss here. The first process is moving average process. We consider the first possibility. The process yt has a memory of the shocks corresponding to the past values of y. But it does not have memory corresponding to the past values of y. So yt equal to, you take a constant mu here, then of course present shock is always there, ut is always there, and then it depends upon ut minus 1, ut minus 2, so on, ut minus q. And the corresponding parameters or corresponding coefficients are theta 1, theta 2, so on, theta q. So theta 1, theta 2, theta q are the constants which may be positive or negative. So ultimately, this process has q plus 2 parameters, all the thetas, q thetas, mu and sigma square u. And this process is called the moving average process of order q, because it has memory of past shocks up to lag q, ut minus q. So it is a moving average process of order q. Mu is also called the long-term mean. And you can write the process in this form: yt minus mu equal to summation j equal to 0 to q theta j ut minus j, where we take, for corresponding to j equal to 0, you take theta naught equal to 1. And this is actually the moving average of white noise ut. That's why this process is also called the moving average process. Say how we proceed in taking moving average. Say, suppose you have a series x1, x2, x10. Then you want to take a moving average of period, say 5. Then first you take from x1 to x5, then you take x from x2 to x6, and so on. This is how you proceed in taking moving averages. Or this is how we are proceeding here also. So that's why this process is called the moving average process. Process does not have memory of exactly where it was, but it does have memory of random noise corresponding to where it was, or the random noise corresponding to the past values of y. You can easily obtain the mean of the process, which is mu. Variance of the process can be calculated. Again, I am not going into the details of the derivation. You can also calculate the autocorrelation function or autocovariance function of the process. So suppose you take MA1 process, you take Q equal to 1. So you get this process, and then variance of the process is sigma square y equal to sigma square u1 plus theta 1 square, and autocovariance function is like this. Now here, what you observe that gamma 1 is equal to theta 1 sigma square u, and gamma 2 is 0. In fact, gamma k is equal to 0 for all k greater than 1. Now, this is a specific feature of moving average process. So for MA1 process, after Q equal to 1, gamma k becomes 0. After k equal to 1. Similarly, rho k also becomes 0 for after k equal to 1. Then we have this simulated data for the MA1 process for different parameter values. I have plotted this simulated data on MA1 process with theta 1 equal to 0.7. Now, if you take the ACF of MA1 process for theta 1 equal to 0.7 and for theta 1 equal to minus 0.7. Of course, for k equal to 0, it is 1. Then for k equal to 1, you get this significant value. And after that, it becomes 0. If theta 1 is minus 0.7, then this value is negative. And after that, it becomes 0. Similarly, if you take q equal to 2, means you take moving average process of order 2. Then again, if we plot the ACF of MA2 process, then gamma 0 is equal to 1. Gamma 1 takes this value, gamma 2 takes this value. After that, it becomes 0. Sorry, in fact, I have plotted rho k here. So rho k is equal to 1, for k equal to 0, then for k equal to 1, you get this value, for k equal to 2, you get this value, and then it becomes 0. So this is a specific feature of moving average process. For MA2 process, you observe that after k equal to 2, the ACF is 0. Now this property actually helps you in identifying the moving average process. Now, before moving to autoregressive process, first I am going to consider random walk model. Now, suppose UT is a purely random process with mean 0 and variance sigma square u. Then we define the random walk process as yt equal to mu plus yt minus 1 plus ut. So suppose you start from y naught equal to 0. So what is y1? y1 equal to mu plus u1. y2 is equal to mu plus y1 plus u2. Then we substitute the value of y1 from the previous equation, and so on. So by recursive substitution, after t steps, you observe that yt is equal to t mu plus summation I equal to 1 to t ut. Now, if you look at this equation, because of this term, say t mu, This is a linear function of t. So if you plot yt, it appears that the process has a linear trend. So you may confuse a random walk model by a time series having a linear trend. Often in practice, in many practical applications, you observe this kind of time series. The process is said to have a stochastic trend. And if you take expectation of yt is equal to t times mu, variance of yt is equal to t times sigma square u. So here you observe that, remember, initially we have assumed that mu t is equal to mu. So mean of the process does not depend upon t. And then we have also assumed that the variance of the process does not depend upon t. But here the process mean depends upon t, the process variance also depends upon t. Now, what you expect, how the process is going to behave? As t increases, this term increases, and suppose mu is equal to 0, then you get 0 here, right? Now, how the variance is going to behave? As t increases, t times sigma square u, this is going to increase. So you can say that the process explodes. It has a very large variance. Its variance becomes larger and larger as t increases. It means as the time progresses, you expect a lot of variations in the time series. In fact, the variance tends to infinity as t tends to infinity. So as the time progresses, you say that the process explodes. It has a very large variance. It fluctuates a lot. So this is a specific feature of the random walk model. In economic time series, say in practice you will get several time series which behave like a random walk, like share prices, real exchange rates, etc. So it is very important to check or to test whether your time series is a random walk or not. Its behavior is entirely different. Remember one thing, suppose you are running a regression between two time series. Now in regression, what we assume, what is the formula for regression coefficient? R sigma y upon sigma x. So we assume that both variances sigma y and sigma x are finite. So if you are going to run regression between two time series which are non-stationary or which are behave like a random walk, then you cannot use simple regression techniques for those time series. Again, I am not going into much details here, but these are the graphs of random walk models. Here I have taken mu equal to 0. Here mu is equal to 0.1. So it is a small value, but the behavior of the time series is entirely different. And it appears that the time series has a linear trend. Such kind of trend is called a stochastic trend. It is because of the presence, means if you have studied time series earlier also, then you may understand what I am saying. It is because of the presence of unit root in the time series. or it is because of the non-stationary behavior of the time series. Now I come to the autoregressive process. In autoregressive model, we regress current value of variable on past values. Then uses regression of the variable against itself, means yt depends upon yt minus 1, yt minus 2, yt minus 3, etc. It uses regression on the variable against itself. So that's why it is called autoregression or autoregressive process. So it predicts future behavior based on the past behavior. And then you can use it for forecasting purpose if there is correlation between current and preceding values. Then an autoregressive process of order P, or it is also denoted by ARP process, is defined as yt equal to phi1 yt minus 1, so phi p yt minus p plus delta plus ut. Again, ut is a purely random process. It has mean 0, variance sigma square u. And these phi's are the parameters. Then you have delta also as parameter and sigma square u. So in all, there are p plus 2 parameters. You can obtain the mean of the process. And now let us come to the AR1 process. You take p equal to 1. This process is also called the Markovian process, because the Markovian property is that given yt minus 1, yt becomes independent of yt minus 2, yt minus 3, so on. So given yt minus 1, yt does not depend upon yt minus 2, yt minus 3, and so on. So this is the Markovian property. So that's why this process is also called the Markov process. Then this is the mean of the process. I have simulated data from AR1 process and plotted it. Then you can calculate the variance of the process also, ACF, ACVF. This is the autocovariance function. This is the autocorrelation function. Now, if you look at the autocorrelation function, and in fact, we assume that mod of phi1 is less than 1. Remember that for phi1 equal to 1, if you take phi1 equal to 1 here, you get the random walk model, which is non-stationary. And for the stationary purpose, you require this condition, mod phi1 less than 1. And if mod phi1 is less than 1, as k increases, this rho k declines geometrically. It does not become 0, but it declines geometrically. Now, this is the ACF of AR1 process. It never becomes 0, it declines geometrically. Now, remember, in MA1 process or in moving average process, it becomes 0 after a certain point. In AR process, it never becomes 0. It declines geometrically. Similarly, you can consider AR2 process also. You can obtain its autocovariance function and autocovariance and autocorrelations also. So for MA processes, the correlogram vanishes after a certain point. For AR process, it declines but never vanishes. So you can use this property for identifying moving average and autoregressive processes. Uh, another thing which you can use is partial autocorrelation function. Now this is the ACF of MA1 process. This is the ACF of Ma2 process. So it becomes zero after a certain point. Whereas this is the partial autocorrelation function. It becomes negative here, again positive, positive, and so on. So it declines but never becomes zero. Similarly here also for Ma2 process, it never becomes zero. So for moving average process, if you look at the ACF, it becomes zero after a certain point, but the partial autocorrelation function, it never becomes zero. It diminishes, it declines geometrically, but it never becomes zero. So this is a specific feature of moving average processes. On the other hand, for autoregressive processes, if you look at the ACF, if you plot the ACF, it declines geometrically, but it never becomes zero. On the other hand, if you consider the partial autocorrelation function for k equal to 1, I have not plotted it for k equal to 0. For k equal to 0, it is always 1. For k equal to 1, you get this value, and then after that, it becomes 0. Similarly here for AR2 process. For first two values, it is non-significant, it is non-zero. After that, it becomes 0. So you can say that the partial autocorrelation function of autoregressive process is somewhat similar to the autocorrelation function of moving average process. Now, sometimes it is more convenient for you to express your data as a mixed autoregressive moving average process. So your model has both autoregressive terms as well as moving average terms. Uh, we write it as ARMA process. And suppose it has P autoregressive terms and Q moving average terms, then we denote it by ARMA PQ process. So ARMA PQ process contains P autoregressive and Q moving average terms. The model for ARMA PQ process is Yt equal to delta plus y1 yt minus 1 plus so on plus yp yt minus p. So you have P autoregressive terms. And then you have ut minus 1, so on, ut minus q moving average terms. Actually, in practice, sometimes if your process is an autoregressive process of very high order or moving average process of very high order, then you can approximate your process by a mixed ARMA process of lower order. And lower order means it has lower number of parameters. So it is always preferable to consider a model which has a smaller number of parameters. Now there are some properties of this ARMA representation which I will just mention. I am not going into the details of derivation. It approximates the dynamic of any purely non-deterministic weakly stationary process. You can easily prove, not easily, derivations are difficult, but you can prove these results. Then it describes a weakly stationary process in terms of two polynomials, one for AR and the other for MA. And higher order autoregressive or moving average process with large number of parameters can be approximated with lower order ARMA process with lesser number of parameters. Then we consider this ALMA 1 process with delta equal to 0. Then these are the expressions for the autocovariance function. Gamma 1 is this. Then after that, you observe that gamma 2, so on, gamma k, all these autocovariances have formula very similar to the autoregressive process of order 1. Because notice that moving average process has effect up to gamma 1. After that, in the autocovariance function, the effect of moving average term vanishes. uh, Here I have plotted the ACF and PS, ACF of ALMA 1 process for different values of phi and theta. Another problem is estimation of parameters. Then for estimation of parameters, one can use the method of least squares or method of maximum likelihood. And nowadays, if you consider any statistical software like Strata or SPSS or reviews, then you can use that software for estimating the time series model. Can we stop for 2-3 minutes?
Yeah. Am I audible? Hello. Yes, sir. Am I audible?
Yeah.
Yeah. If anybody having a question, you can ask right now.
Still we have.
With a question?
Sir, am I audible?
Yeah, yeah.
Yes.
Yes. So I'm Kirti. I'm basically an
Uh,
architect and
just a
planner.
minute. Shikhar, means, I have some more material to present. So should I take questions right now or after some time? Means after the end of the talk. Hello?
Hello.
Yeah.
Anybody having a question, or can we take after that one?
Yeah, means just
After the talk.
I 15, 20 minutes. Then after that, okay.
Anybody? Anybody having a question?
Once again,
Should I start?
Once again, I, Chavi Tiwari, deem it to be my privilege to propose the vote of thanks for today's immensely informative event. On behalf of all of the Department of Computer Science, I'd like to extend our gratitude towards our speaker, retired Professor Anoop Chaturvedi, sir, for taking out time from his busy schedule for us. Sir, thanks to you that this event's been a great learning experience for all of us. I take this opportunity to thank our program coordinator, Dr. Vinay, for the moral support and constant encouragement. And I'd also like to thank the teacher coordinator of this event, Dr. Shikhar Tyagi, for the guidance. And I'd also like to thank all the faculty members of Department of Computer Science and Statistics for the support rendered directly or indirectly. A heartfelt thanks to the students of the department who have enthusiastically been a part of this event. I thank all of you for making this memorable and interesting event a possibility. Hope you have a great day ahead. Thank you.
Yeah, any question?
Good afternoon, sir. My name
Yeah.
is Abhishek Sharma. Sir, I have one question that how to collect the data sets for these type of time series related questions. Sir, because I am also doing some projects related to time series, but not able to find a good type of data.
Uh, what is your objective?
Sir, basically related to finance and marketing and also on stocks, sir. So these three are my basic domains.
Mhm. Then a lot of data is available. So, what kind of time series you want to analyze? It depends upon your objectives. You can get the stock market data on different financial variables. Also, can get data. You can get daily data, or whether you are interested in weekly data. So, uh, it depends upon your objectives. What sort of objective you have in your mind? Hmm. I mean, so
Okay,
many
sir.
things I cannot tell you. You have to decide, keeping in view your objectives. Say one may be interested in minute-to-minute data, or second-to-second data, or one may be interested in monthly data. So period, you have to decide. Then on which variable, whether you are interested in closing price of a particular stock, or the opening price of a particular stock, or the whether you are more interested in daily variation. So accordingly, you have to collect data. Means
Yes, sir.
as such, I can't say that you have to collect data on this variable, or uh, this should be the period. Ultimately, it depends. You have to decide, keeping in view your objective.
Okay, sir. Thank you
Hmm.
very much, sir.
But nowadays, availability of data is not a problem. Yes, of course, uh, then you have to decide tools also, keeping in view your objectives.
Thank you, sir. Sir, can you please explain something about co-integration to us?
Okay. You remember during the talk I mentioned about van der Waals model?
No, sir. Sir,
Uh,
you talk about white noise only.
no, van der Waals also.
Random walk.
Yeah.
Yes, sir.
I also mentioned that when you want to run regression between two time series, which have unit root or which are non-stationary, to random walk time series, then usual regression techniques don't work, right?
Yes,
So
sir.
how to proceed? Now there are two possibilities. Both the random walk or both the time series are moving in the same direction or almost parallel to each other. Just think about that. There are two non-stationary time series which are moving parallel, almost parallel to each other. Then we say that both the time series are co-integrated, and then it is possible for you to predict one time series on the basis of other time series. If both the time series, which are non-stationary, are moving in different directions, and then if you try to predict the value of one time series on the basis of other time series, then your long-term predictions will not be accurate because both the time series are non-stationary and moving into different directions. So then the time series are not co-integrated. So basically we go for co-integration analysis when your time series has unit root. So first you test for the unit root. If both the time series have unit root, then you go for co-integration analysis. To discuss co-integration analysis in details requires at least one or two lectures. First, but this is the basic idea behind co-integration.
Yes, sir. Thank you, sir.
So, means this is the step which you should follow. First, you test for the unit root. If both the time series are stationary, then you should go for causality test. And if both the time series are non-stationary, then you should test for the co-integration. Then you should go for co-integration analysis, right?
Yes, sir.
Good afternoon, sir. Good afternoon, sir. Sir, my doubt was that if there are two time series given to us, then how can we find, is there any method to find a lag between those two time series? We know that they are collinear in real scenario. I'm talking about financial markets. For example, uh, if there is a time series of US bond yield and then our Nifty. So we know that there is some relation between them. But if we want to find the lag in which the effect is the spillover effect, which comes to the, which is seen over the Nifty by US bond. So if we want to calculate the lag between them, what method we to follow or something like that?
Yeah. So basically, you are interested in causality, right? Whether the causality is instantaneous means it has immediate Means whether the current value of one time series is affected by the current value of other time series, or it is affected by the past values of other time series, or it is affected by the current and past values of other time series, or if it is affected by the past values of other time series, then what should be the lag, right? Uh, so you should go for causality analysis.
Sir, may you repeat what should we apply?
Means basically you are interested in causation, right? You have two time series, and you are interested in whether the value of a particular time series is instantly affected by the current value of other time series, or it is affected by the past values of other time series. And if it is affected by the past values of other time series, then what should be the lag? Means, what should be the appropriate lag, right? Then you should go for the distributed lag models or causality analysis. You may consider error correction models.
Okay, sir. Thank you.
Sir, um, uh, hello, sir.
Yeah.
Yes. So, sir, I am basically an architect and a planner. So, we are mostly engaged in doing long-term projections. So, right now, what I'm trying to do is I'm projecting future tourist footfall in an Himalayan state. Now, in that case, what I'm trying to do is I'm comparing certain models, Arima, then I have hot winters, and then traditional decomposition methods. In that, so what I'm doing is I only have data till so much year, like till 2019, I have real data because after COVID hit, the data is something else and it cannot be used for projection. It is giving such wrong results. So I'm taking data till 2019. So is there a time extent up to which I can do prediction? As in, because I want data till at least 2031. So can I use data from 2008 to 2019 to predict 2031? Is it possible?
Yes, of course you can predict, but this is a long period. It's almost 8 years.
11. Yes.
Yeah, no, after 2009, yeah, it is 11 years. So yes, I'm not sure how accurate your projections will be,
Sir,
but
according to MAP and those errors that we see, RMSE values, MAP values, the errors are falling under what is standard acceptable range. But as if I have to write a paper on it and get it published, so will the reviewers accept that I have used so much data and I have extended that data for another 10, a decade? So is it acceptable in the research domain? Is it publishable?
now that's the problem is in 11 years, so many factors are going to affect. Means the kind of infrastructure may change.
Yes.
So is you are analyzing the time series just on the basis of past data. You are not considering any other variable.
No, sir.
What was the past infrastructure, or how the infrastructure, say roads or other things have changed.
Right.
So
No, sir. There's only one variable, that is tourist arrival numbers. That's
Yeah,
it.
yeah. So I'm not sure.
Okay. So, sir, one more question is, have you, I mean, I've not checked your profile so far, but is there anything that you have written about structural breaks in time series data that I can refer to?
Yes, I have done some. Most of my work is theoretical.
Okay.
So it's, so in theoretical work, of course, I have done
I see. Okay.
in the context of time series as well as in the context of regression models
Mm.
or dynamic models.
Okay.
But frankly speaking, I am not an applied man. So,
But that's okay, sir. I'm only considered in the sense of research purpose and publication. I'm really interested because I'm a planner, and we still use in the reports, we still use those annual growth rate equation and compound annual growth equation. We still are handicapped to such techniques that can actually give us a little accuracy while predicting and forecasting. So I just wanted to experiment, and somehow I'm getting it. It's just that I'm not sure if I can use such data and project it for a decade. How valid is it? Even in research, application is another thing. So,
say in the context of your problem, say tourist data,
yes, sir.
if you have data for different tourist destinations, and if you also have data on the development of infrastructure, means
Okay.
then probably you can have better results. Means the areas which don't have developed infrastructure, don't have road connectivity, etc. What kind of changes are there in those areas or the areas which
Okay.
have? So it means then probably you may get more accurate or better results.
All right. I understood. Thank you so much, sir.
Hello, sir.
Yeah.
Thank you so much, sir. I think our questions with our students are done. So we can end the session, sir. Thank you so much for your time, sir.
Thank you.
Thank you so much, sir, for your contribution and for your uh, that informative talk, sir. Hopefully, students will be beneficial with this.
Okay, thank you.
Thank you so much, sir. I will get you on this very soon regarding all these things. Government.
Okay, okay.
Thank you. Thank you so much, sir.